Good morning. Welcome to our third lesson. This week we're going to cover the following topics: polar coordinates, conic sections, and three-dimensional Cartesian coordinates. Last week we talked about Cartesian coordinates in the plane, a way to describe the position of a point using XY coordinates. Now we're going to talk about a different way to describe the position of a point. Using polar coordinates, we can describe the position of the point P using two numbers, a number r and an angle theta. R means the distance from the origin to the point. That's the length of this blue line, and theta is this directed angle between the blue line and the x-axis. When we measure this angle, if we measure the angle anti-clockwise, we use a positive number for the angle. If we measure this angle clockwise, we use a negative number for the angle. Think about it like this. Let's imagine that we start with a ruler with 0 at the origin. And you will notice that this is a special mathematical ruler which includes negative numbers as well as positive numbers. And let's suppose that we rotate this ruler. Suppose we always keep 0 at 0, but we rotate the angle. We rotate the ruler. Let's say we rotate the ruler by an angle of plus 45 degrees. Then we can measure along the ruler, and we can label each of the points along the ruler using polar coordinates. For example, if the distance between the origin and the point is 1, then this point has polar coordinates 145. This point has distance from the point to the origin 2, and the angle of the ruler is 45 degrees, so this point has polar coordinates 245 degrees. And for example, this point just here has polar coordinates 3.4, distance from the origin to the point 3.4, and the angle is 45 degrees. We can also use the negative numbers on the ruler. This is the point minus 145, this is the point minus 245, this is the point minus 345, etc. Put the ruler back in its original position, and this time I want to rotate the ruler clockwise. Let's suppose I rotate the ruler by an angle of 30 degrees clockwise. Because we are rotating clockwise, we say that the angle is a negative number. So we're going to use the angle minus 30 degrees. And then we can label all of the points along the ruler: 1 minus 30, and then 2 minus 30, 3 minus 30, etc. And also the negative numbers: minus 1, minus 30, minus 30, etc. And the origin has distance 0. This is 0 minus 30 degrees. Or on the previous one, this is 0, 45 degrees, etc. Origin always has distance 0, but we can use any angle that we want. For example, this is the point where the distance between the point and the origin is 2, and this angle is 30 degrees. So the polar coordinates of this are 230. But you will notice that there is a different way to measure this angle. I suppose instead of you taking the anti-clockwise angle, I want to take the clockwise angle. Always start at the x-axis and then go around until we meet this blue line. Now this angle is minus 330 degrees. This point also has polar coordinates 2, minus 330. Or there's another way to do this. Let's suppose we go anti-clockwise, but let's suppose we don't stop at the angle. Let's suppose we go all of the way around like this, 360 degrees, and then another 30 degrees. In other words, we could take the angle 390 degrees. This point also has polar coordinates 390 degrees. Here's another example. First of all, let's use the angle 210 and then draw this red line. The length of this red line is 2. So this point has polar coordinates 2, 210. But there's another way we can do this. Instead of using a positive distance, we might use the negative part of the ruler. Suppose instead we only rotate by 30 degrees. And then imagine that we have our ruler like this. And then we have the number 1, the number 2, etc. Number -1, and just here we have -2. This point also has polar coordinates -2, 30s. You will note that there's many ways, in fact, infinitely different ways to write the polar coordinates. For example, find all of the polar coordinates of the point to 30 degrees. Picture, there's 230 degrees. This angle is 30, so it's going to be here. Now, as we've seen on the previous example, we can either use a positive distance, r is 2, or we could use a negative distance, r is -2. But I want to look at what happens if r is equal to 2. R is equal to 2, we know we could have the angle 30 degrees, or we could go all of the way around like this. We could have 390 degrees, or 30 plus 360 degrees. Or we might go around like this. That's 330, so minus 330 degrees. In other words, 30 minus 360 degrees. Or what else could we do? How else could we measure this angle? Maybe we go around 2 times like this. Go around 2 times is 720 degrees, and then extra 30 degrees gives us 750 degrees, or 30 plus 720 degrees. Or we could go around the other way, 30 minus 720 degrees. Or we could go around 3 times, or we could go around 4 times, or we could go around 5 times. If r is equal to 2, theta could be any one of these angles. Next, what happens if r is -2? Well, we could have 210 degrees. Why 210? Because 210 is 108 plus 30. In other words, 210 points in the opposite direction from 30 degrees. And then, as before, we could do the 210 and then go round an extra time. Or we could go around 2 extra times or 3 extra times, etc. So we could have 210 plus or minus 360, 210 plus or minus 720, etc. Therefore, the answer to this question is the point with polar coordinates 2, 30 degrees has polar coordinates 2, 30 plus 360 multiplied by an integer n degrees, or minus 2, 210 plus 360 multiplied by some integer m degrees. In this red box, I've written every way to write the polar coordinates of this point. We can also draw some graphs in polar coordinates. For example, draw the graph r is equal to a. Remember, r is the distance from the origin. If this distance is always the same, what does it look like if the distance from a point is always the same? It looks like a circle. This circle is r is equal to a. And the radius is the absolute value of a. If a is a positive number, for example, a is 2, then this is just a circle of radius 2. If a is, for example, a negative number, let's say r is equal to minus 2, then again, this is a circle of radius 2. Another thing I might ask is, draw the graph theta is equal to b. Draw all of the points which have angle equal to b. Imagine taking our ruler Suppose we start with our ruler like this, with 0 at the origin, and then let's suppose that we rotate this by an angle b. We would have something like this, and then we draw along the ruler to get the graph. We're going to be drawing a straight line which passes through the origin and which has an angle to b. To summarize, r is equal to 1 and r is equal to minus 1 are two different equations for the same circle. Circle of radius 1 centered at the origin. Theta equal to 30 degrees, theta equal to 210 degrees, and theta equal to minus 150 degrees are all equations for the same line. That's this line. Another example. Draw the set of points polar coordinates satisfy the following rules. R is between 1 and 2. Theta is between 0 and 90 degrees. Let's start with r equal to 1. R equal to 1 is a circle. Looks like this. Then we can look at r equal to 2. R equal to 2 is also a circle. There we go. Theta equal to 0. Change color. Theta equal to 0. We know where this is. That we know it's this line just here. Theta equal to 90 degrees. We know this line. We are asked to draw a set of points which are between these lines, between the two circles, between the orange line and between the red line. In other words, we're asked to draw this region, which I'm coloring in here. Let's draw this with a computer. Here we go. Another one. Draw the set of points whose polar coordinates satisfy the following rules. R is between -3 and 2. Theta is equal to 45 degrees. Let me start with the angle first of all. Theta is 45 degrees. This is straightforward. Theta is equal to 45 degrees. R is less than or equal to 2. 2 is about here. R is greater than or equal to -3. -3, we're looking down the bottom left-hand corner. -3 is about here. We should be on this blue line between the two orange ones. So we should have something like this red line. Let me draw this with a computer, and here we are. Draw the set of points whose polar coordinates satisfy the following rules. R is less than or equal to 0. Theta is equal to 60 degrees. And I'm going to do the angle first. 60 degrees out here. But we don't want this whole line. We only want the part of the line where R is negative. So in fact, we only want the bottom left part of this, which goes all of the way to -infinity. Here we are. And fourthly, draw the set points whose polar coordinates satisfy the following. Theta is between 120 and 150 degrees. So first of all, where is 120 degrees? This is 0. The x-axis is 0. Y-axis is 90 degrees. We need another 30 degrees. So we should be about here. There's 150. 150 should have another 30 degrees, like this. This is 150 degrees. And we're interested in the set of points which are between these lines. So we can colour it in, this part and this part. Let me use the computer now. Here we are. We have some nice formulae to relate polar coordinates and Cartesian coordinates. Looking at the picture first, this point P, we could say, has Cartesian coordinates x and y, or polar coordinates r and theta. And from this triangle, we can say straight away that x is the same as r cos theta, y is the same as r sine theta. By Pythagoras, because we have a right angle triangle, x plus y squared is equal to r squared, and tan theta is equal to y divided by x. I've put these at the top of the screen, and I'm going to solve this example. Convert the polar coordinates, -3, 90 degrees, into Cartesians. We're told the polar coordinates, and we're asked to find the Cartesian coordinates. In other words, we're asked to find x and y. We know that x is r cos theta, and we know that y is r sine theta. All we need to do is put the numbers into the equations. We get -3 cos 90 degrees, and then -3 sine 90 degrees. When we calculate this, we get the solution 0 minus 3. Let's quickly draw a picture of this. Zero degrees is the x-axis, 90 degrees is the y-axis, so we must be on the y-axis. We go up for the positive numbers, positive 1, positive 2, positive 3. We go down for the negative ones. So we must be about here. -3, 90 degrees in Cartesian coordinates. Sorry, in polar coordinates, or in Cartesian coordinates, x is 0 and it's -3. We can go the other way as well. Find polar coordinates for the Cartesian coordinates x, y is 5 and 12. This question doesn't say find all of the polar coordinates, it just says what I might write this as convert Cartesian coordinates. So you can choose which one to choose. Many correct answers. But you have a homework question like this, and only one of the correct answers is in the multiple choice. So you need to work out which one I mean. To solve this problem, we could use positive r or we could use negative r. Just to make this easier for me, I'm going to choose positive r. And I'm starting with the formula r squared is equal to x squared plus y squared. Or to say it another way, r is plus the square root of x squared plus y squared. And when we calculate this, we find that r is equal to 13. We also need to calculate the angle theta, and I'm going to use the equation r, so y is equal to r sine theta. We arrange this to the form theta is inverse sine of y over r. Put the numbers into our calculator, and we find the angle is approximately -67.38 degrees. So we could write down the polar coordinates as 13 -67.38. You'll notice that to avoid confusion, every time I write coordinates, I'm either writing xy is equal to some numbers or r theta is equal to some numbers, which I hope makes it clear when I'm talking about Cartesian coordinates and when I'm talking about polar coordinates. Just to make sure that our answer makes sense, we could draw the picture. We know that x is 5, and we know that y is -12, so the point P must be here. And we can understand that if r is 13, then the angle must be a negative number and must be roughly the size. -67 looks about right on the picture. So this confirms that we haven't made a mistake in calculation. If we get a number which is obviously doesn't make sense on the picture, then we know that we've made a mistake and we can try again. That is the end of coordinates. Next, I want to talk about conic sections. I'm not seeing my picture properly here. I think that this OLearn platform has not been able to load this file properly. If you give me a moment, I'll try to load the pictures more clearly. Okay, I hope you can see this now. The idea behind conic sections is to start with a double cone. Start with this thing which is a cone on the top and a cone on the bottom. And we want to slice this in different ways. If we slice this with a horizontal plane, we get the first picture, which is a circle. We take the cone, cut it across. What shape do we have? We have a circle. Next, look at the second picture. If we take our double cone and we slice it using a plane which is sloping a little bit, we obtain an ellipse. Let's suppose we slice our double cone using using a plane which has exactly the same slope as the edge of the cone. Then we get this curve called a parabola. Or finally, if we slice our double cone using a very steep plane, and we look at this red curve, the intersection between the cone and the plane, we get a type of curve called a hyperbola. In this section, we're going to be discussing parabolas, ellipses, and hyperbolas. So now I need to load my slides again. Right. First, I want to talk about parabolas. Where do we see parabolas? One place we see parabolas is if we bounce a ball. Look, see what is the curve of the bounce of the ball. This is a parabola. Another place we see parabolas, or almost parabolas, is on suspension bridges. At this curve, the curve of the ropes. If you become a bridge architect, your engineer will explain to you that this curve is not exactly a parabola because of the way that the forces hang on it. But for our purposes, or if you're drawing a picture of a suspension bridge, we can assume that this actually is a parabola. Another place we see parabolas a lot is on satellite dishes. If you take a satellite dish and draw a line on it, this curve is a parabola. To describe a parabola, we need a point, which is called a focus, and we need a line called a directrix. This point just here is my focus. I'm going to say this has Cartesian coordinates 0, b. And this green line at the bottom is the directrix. I'm going to say that this is a line with equation y is equal to minus b. I want to take all of the points P to satisfy a rule. The rule I want is the distance between point P and the focus. This distance is the same as the distance from the point straight down to the directrix. The rule for a parabola is that the length of the line PF is the distance between F must be the same as the distance between P and Q. So definition, point P is on a parabola if and only if the distance from P to the focus F is the same as the distance from P to the directrix. Now, we can do our calculations. The distance between P and F, using the coordinates on the picture before, we can find is the square root of x squared plus 1 minus p squared. Distance between the point P and the directrix is y plus p. And using the rule that these two must be the same, and rearranging this, and I'll leave this for you to check later, we obtain the equation x squared is equal to 4py. Here's a simplified picture. This blue curve has the equation x squared is equal to 4py. Focus is the point 0p, and the directrix is the line y is equal to minus p. This distance is p, and this distance is p. We might turn our picture upside down. Suppose now we put the focus at 0 minus p. We put the directrix as y is equal to p. And then our parabola has equation x squared is equal to minus 4py. I've just put a minus on everything. So instead of plus 4py, it's now minus 4py. Or I might rotate the picture 90 degrees. Really, in this picture, I've taken the first one and I've swapped the positions of x and y. So instead of x squared plus 4py, I now have y squared is equal to 4px. The focus is the point p0, and the directrix is the point x minus p. Or I might multiply everything by minus 1 to take the reflection. Y squared is equal to minus 4px, has focus minus p0, and directrix x is p. For example, find the focus and the directrix of y squared is equal to 10x. We have the equation y squared is equal to 10x. Out of previous examples, it looks like y squared is equal to 4px, but with p equal to 2.5. As soon as we know this, we can write down the focus and the directrix. Focus is the point p0, or 2.50, and the directrix is the line x is equal to minus p, or minus 2.5. Another example, find the equation for a parabola which has focus 0 minus 10 and directrix y is 10. What can we say here? Clearly, from looking at the focus and directrix, we must have that p is equal to 10. And the equation must look like x squared is equal to minus 4py. So clearly, the answer to this problem must be x squared is equal to minus 40y. Our next type of conic section is ellipses. Suppose we had a piece of string which we pin down using 2 pins, and we draw around using a pencil. The shape that we get is an ellipse. Where do we see ellipses? We see them in the orbits of planets. We see them in architecture. For example, this building in Denmark has an elliptic shaped top. and we see them in mathematics. To describe the ellipse, we need two focuses, or two foci. Focus is one of these unusual words where the plural is not as we expect. We can have one focus or two or more foci. Let's suppose we have a focus at the point minus C0, and we also have a focus at the point C0. That's the same as the two pins in the previous picture where I said, imagine that we draw an ellipse using a piece of string, two pins, and a pencil. The rule for ellipse is the distance from a point P to first focus plus the distance from the point P to the second focus must always be constant, equal to the length of the string. And I'm going to call this number 2a. This is the definition. We must have that the sum of these two distances is always constant. When we start with this, when we put the coordinates in, again, I leave this for you to check. We obtain a standard equation for an ellipse like this. X squared over a squared plus y squared over b squared is equal to 1, where a and b are positive numbers and a is bigger than b. This is an important point to note. A is always going to be a bigger number than b. So let me summarize. This is the ellipse x squared over a squared plus y squared over b squared is equal to 1. Distance between the center, or in other words, the origin, and one of the foci is called the center to focus distance, or C. And the equation that you should be remembering or writing down before an exam is that C is the square root of a squared minus b squared. This is why a must always be a number than b. The foci are at minus C0 and C0. Points minus A0 and A0 are called vertices. I might rotate this graph. What we're really doing is we're swapping x and y. This is an ellipse with equation x squared over b squared, y squared over a squared is equal to 1. Why did I swap a and b around? I swapped them around because I always want to have a the bigger number. And I want to do this because I want to use the same center to focus distance equation. The center to focus distance is always the bigger number squared minus the smaller number squared, and then x squared. The foci are now on the y-axis, 0 minus c and 0 c, as are the vertices, 0 minus a and 0 a. You'll notice that the vertices, the foci, and the center are always on the side. For example, the ellipse x squared over 16 plus y squared over 9 is equal to 1. Out of 16 and 9, we look to see the bigger number. The bigger number is 16, so a must be the square root of 16, it must be 4. And the smaller number gives us b is equal to 3. b is the square root of 9. We can calculate the center to focus distance, a squared minus b squared. That gives us the square root of 7. The center of the ellipse is at 0, 0. The foci are minus C0 and C0, so that's plus and minus square root of 7, 0. And the vertices must be minus 4, 0 and 4, 0. Another example. X squared over 16 plus y squared over 25 is equal to 1. The two numbers now are 16 and 25. Which is bigger? 25 is bigger. So A must be 5 and B must be 4. Then we can calculate the center to focus distance, must be 3. Center is always 0, 0. And the foci are 0, minus C and 0, C. Or 0, minus 3, 0, 3. Vertices, we use A. Vertices must be at 0, minus 5 and 0, 5. Hyperbolas. Where do we see hyperbolas? In architecture, we might see them on cooling towers of power station. These curves I've just drawn are hyperbolas. Or this building in Japan is designed using hyperbolas. Let's look at the pictures we did before. Again, we need two foci, which I'm going to use the same coordinates as before, minus C0 and C0. This time we have a slightly different equation. For an ellipse, we had a plus in the middle. For hyperbola, this must be minus. The difference between the distance from P to the first focus and the distance from P to the second focus must always be constant. And the constant I'm calling 2A. And then because we don't know which one of these two curves we're on, we might be on the left curve or we might be on the right curve. We don't know which one of these numbers is bigger, so we have to add these absolute values so that 2A is always a positive number. This is the rule. A hyperbola must satisfy this rule that the difference between these two distances must equal to 2A. When we run through the calculation, I'll leave this for you to check, not all the details are here. We obtain the standard equation for a hyperbola. And you'll notice this looks similar to the equation for an ellipse. An ellipse we had plus in the middle. For hyperbola we have almost the same equation, but now we have minus just here. For hyperbola, it doesn't matter if A is bigger than B or if B is bigger than A. It doesn't matter which one of these is bigger. It doesn't matter because now the center to focus distance is square root of A squared plus B squared. You will recall that for an ellipse, we had a minus sign just here. And to make this work, A must all, we had to have that A was bigger than B. For hyperbola, it's a plus sign here, so it doesn't matter if A is bigger than B or if it's bigger than A. And then foci and the vertices are as we expect. Minus C0 and C0, minus A0 and A0. The center to focus distance is an important equation to remember for an exam. Make sure you've got this written down before you start an exam on this course. And make sure you remember that for ellipses it's squared minus b squared. For a hyperbola it's a plus in the middle. We might also rotate everything 90 degrees. Instead of x squared over a squared minus y squared over b squared equal to 1. We swap the positions of x and y, so now y squared over a squared minus x squared over b squared is equal to 1. Center to focus distance equation is the same. Foci are now at 0, minus c and 0, c, because they're on the y-axis, and the vertices 0, minus a, 0, a. For example, the hyperbola x squared over 4 minus y squared over 5 is equal to 1. Four is a squared, so a is 2. 5 is b squared, so b must be the square root of 5. Where is the center? The center for all of these is at 0, 0. The center to focus distance, the square root of a squared plus b squared, we can calculate is equal to 3. And as soon as we know the center to focus distance, we can write down the foci minus 3, 0, 3, 0. And we can use a to give us the vertices, minus 2, 0, and 2, 0. Hyperbola y squared over 9 minus x squared over 16 is equal to 1. Now I have y in the first position, x in the second position. First number is a squared and the second number is e squared. Remember, it doesn't matter which one of these is bigger. For a hyperbola, the first one is a and the second one is b. So a is 3 and b is 4. We can calculate the center to focus distance is 5. So we know the foci, 0, minus 5, 0, 5. And we use a, that's the first number, to give 0, minus 3 and 0, 3. If you're confused as to the vertices, imagine that you put x is 0. So in other words, imagine that this thing is all 0. Then we get y squared over 9 is equal to 1. That's the same as saying y squared is equal to 9. And when we solve this, y must be minus 3 or y is equal to 3. Why are we interested in these conic sections? They're useful in architecture and engineering because of their reflective properties. First of all, a parabola. Parabola has this special property that if we shine light waves, sound waves, or something onto a parabola, and then we take the reflection, if these are all straight coming down, they reflect to the focus. Or to say it a different way, if we start at the focus and we shine a light or sound or something onto the parabola, it is reflected out of the parabola as straight lines. How's that useful? Well, it's useful in, for example, car headlights. Let's suppose we put a light at the focus of a parabola, and on the parabola we put a mirror. And the light from the lamp shines onto the mirror and then is reflected out of the car, all pointing forwards in straight lines. Or this is used on satellite dishes. Let's suppose your signal is coming in from a satellite. We have some satellite up here in space, streaming down a Digitex signal or whatever it is you're watching. The signal comes down, bounces onto your satellite dish, and then is reflected towards the receiver of the satellite dish, which takes the signal. Go back to this picture. This receiver just here is placed at the focus of the hyperbola. Or perhaps more relevant for architecture is this idea of using a concrete parabolic dish, putting a person sitting with their head at the focus. And then a long way over to the right, we do another one. We have some sort of person sitting in front of a concrete dish with their head at the focus. One person talks, the sound of their voice is bounced off the dish towards the other dish and then to the second person. This picture is taken in San Francisco. They have two of these dishes at a distance. Two people sit in these seats. They can talk to each other. And the ellipse has reflective properties as well. It has the properties that sound or light waves which start at one focus are reflected off the ellipse to the other focus. So, for example, if we build a room in the shape of an ellipse, it's called a whispering gallery. We have two green people stand at the sky. These two people can talk to each other even if the room is crowded, because their voice is reflected off the walls perfectly to the other person. There's another picture. This is a subway tunnel which is drawn in the shape of an ellipse. Here the red person can talk to the blue person because their voice is reflected off the walls of the tunnel. The most famous elliptic room in the world is probably this one, America. And the architects of this building, which I'm sure you know where it is, the architects of this room studied their conic sections in their maths class, and they designed this room such that the desk and the seat is placed at one of the foci of the ellipse. Hyperbola also has reflective properties, and I've just drawn one half of a hyperbola here. This has the property that if we shine light or sound waves towards a focus, it's reflected to the other focus. These properties are also used in telescopes. This is a diagram of a very simple telescope. One just 2 mirrors. More complicated telescopes would have more mirrors, but this one is just drawn with 2 mirrors. First of all, we have parabola just here, which has a focus roughly here. Light shining into the telescope is reflected towards the focus of parabola. Then we have a hyperbola. Mirror just here is a hyperbola. Focus of a hyperbola is here, and the other one is the same focus as a parabola. Light which is shining towards the right-hand focus is reflected towards the left-hand focus. Just using 2 mirrors, one in the shape of a parabola, one in the shape of a hyperbola, and putting the foci in the correct positions, you can build a simple telescope like this. Our final topic for today is the topic of 3-dimensional Cartesian coordinates. 3-dimensional space we call r to the power 3, because effectively we have 3 real lines, and we can describe the positions of points in 3-dimensional space using 2 coordinates. We have an x-axis, a y-axis, and a z-axis. The point where these 3 axes cross is called the origin. And then we describe the position of all of the points in 3-dimensional space using the x-coordinates, the y-coordinates, and the z-coordinates. For example, if we look at, say, this orange point, it has x-coordinate is equal to 1. start at the origin and go 1 along the x-axis. Second coordinate is 0. We go 0 along the y-axis. And then we go up 2 because z is equal to. When we talk about three-dimensional space, we use a left-handed coordinate system. What I mean is, imagine you take your left hand and you hold it like this. You can see in the video how I'm holding my hand. Using your left hand, we count from the bottom, x coordinate on the second finger, y coordinate on the first finger, and z on your thumb. Anytime we draw axes in three-dimensional space, we use our left hand to understand that the x-axis is pointing this way, y-axis is pointing this way, and then z-axis is pointing upwards. We can talk about planes in three-dimensional space. For example, the plane z is equal to 0. All of the points x, y, z, where z is 0. X can be any number, y can be any number, but z must be 0. We get this blue plane. Green plane is all of the points where x is equal to 0, and the red plane is all of it where y is equal to 0. Or we might be interested in different numbers. For example, let's suppose we look at z is equal to 5. That's all of the points where x is any number, y is any number, and then z must be 5. Or we might look at the green plane, all the points where y is equal to 3. Or we might be interested in where the two planes intersect. They intersect in a line where y is equal to 3 and z is equal to 5. X can be any number. Example. Which points, x, y, z, satisfy these two equations? X squared plus y squared is equal to 4. This is a circle, right? X squared plus y squared is equal to 4. Must be a circle of radius 2. And z is equal to 3. Z is equal to 3 we know is a horizontal plane. And we know that x squared plus y squared is equal to 4 is a circle. Putting these together, this blue plane is the plane z is equal to 3. We know we must be in this plane. And x and y must be on this, must give us the circle. So we have this red circle which is floating up in the z is equal to 3 plane. We can measure distance in three-dimensional space. As I said before, the set of all of the points x, y, z. X is any real number, y is any real number, z is any real number. We have real number, real number, real number, or real R cubed, real numbers cubed. This set is called R3. And just as we did in R2, we can measure the distance between any two points. This is the formula. Distance between P1 and P2 is the square root of x squared minus x1 squared plus y2 minus y1 squared, z2 minus z1 squared. So, for example, what is the distance between the point 215 and the point minus 230? Use our equation. Minus 2 goes here, and then minus 2 from here. I use 3 and 1 to get 3 minus 1. And then I'm using 0 and 5 to get 0 to 5. When we calculate this, we find the answer is 3 square root of 5. And our final topic is the topic of spheres in three-dimensional space. Suppose we have a sphere. Suppose that the center is at the point x0, y0, z0. And let's suppose that the radius of the sphere is equal to a. If P is some point on the surface of the sphere, then the rule is that distance between the P and the center of the sphere must be equal to the radius a. Using this equation, putting the coordinates in, we find that the standard equation for a sphere of radius a, centered at the point x0, y0, z0, is x minus x0 squared plus y minus y0 squared plus z minus z0 squared is a squared. And the type of questions I might give you are: find the center and the radius of the sphere. X squared plus y plus z squared is equal to 3x minus 4y plus y is equal to 0. Now, wait a minute, that doesn't look like this. It's a slightly different form. First thing we need to do is we need to change our equation so that it looks like the standard equation. After we get the standard equation, we can then read off x0, y0, z0, and a, and then we've answered the question. So we're going to take this equation and we're going to rearrange it. And we do it like this. We're going to start with the equation I've given, and we're going to use this property, which I had in red. Remember that x minus b squared is equal to x squared minus 2b plus b squared. First thing I want to do is I want to put all of the x terms together. I have x squared and 3x. Put these together. There's just a y squared right here. And look at the z terms. There's a z squared and a minus 4z. Put that here. And all of the numbers, the plus 1, I'm going to move to the other side to become minus 1. And I'm going to use this property. Now, note that there's a minus 2b here and there's a minus b. In other words, this number is going to be a half of this number. I have 3 just here. 3 is going to be, let me try to get, I have a 3x. That must be the same as minus 2b. That tells us that b must be, let me write that, 2b must be the same as 3. B must be 3 divided by 2, and then b squared must be 9 divided by 4. What I'm going to do is I'm going to add 9 over 4 and then subtract 9 over 4. Exactly the same number, add it on and then subtract it, we still have the same equation. And I'm going to do the same thing on the z terms. I'm going to do plus 4 and then minus 4. These numbers, the 9 over 4 and the minus 4, I don't need, so I'm going to move these off to the right side. And we're left with x squared plus 3x plus 9 over 4 plus y squared plus z squared minus 4z plus 4 is equal to minus 1 plus 9 over 4 plus 4. And because we've added on and subtracted 9 over 4, this first bracket you'll notice is exactly the same as x plus 3 over 2 squared. And because we've added on and subtracted 4, you'll notice that the final bracket is exactly the same as z minus 2 squared. Now we can read off the answer to this problem. It should be minus x0. Minus x0 is the same as plus 3 over 2, so x0 must be minus 3 over 2. In the final bracket, we should have z minus z0. So z0 must be 2. And in the middle bracket is just y squared. So y0 must be 0. The center of the sphere must be minus 3 over 2, 0, 2. And for the radius, we look at the right side. The radius squared is 21 over 4. So the radius of our sphere must be root 3 root 7 divided by 2. And that is the end of today's lesson. Next week, we're going to talk about vectors, dot product, and cross product. If you have any questions, you can type them in the chat now. Certainly. Let me find the file. Okay, the first thing to remember is even numbers and odd numbers. Even numbers are numbers 2, 4, 6, 8, 10, etc. And the odd functions are the functions 1, 3, 5, 7. So odd numbers 1, 3, 5, 7, 9, etc. We also have even functions and odd functions, or functions which are not even and not odd. The rule to remember that is that if we take even numbers, 2, 4, 6, 8, 10, etc., and instead we look at the functions x to the power 2, or x to the power 4, or x to the power 6, or x to the power 8, etc. These are all even functions. If we do x to the power of an odd number, for example, x to the power 1, or x to the power 3, or x to the power 5, etc. These functions are all odd functions. X to the power of an even number is an even function. X to the power of an odd function is an odd function. That's an easy way to remember it. What does an even function mean? An even function means that f of minus x is always the same as f of x. In other words, for an even function, the left side and the right side of the graph should be the same. So for example, if the right side of the graph looked like this, the left side must also look like this. This graph is an even function. For an odd function, the rule is that f of minus x is minus f of x. In terms of the graph, if the graph looks like this, say, then the left side of the graph should be the same shape, but it should be rotated around 180 degrees. So an odd function should look something like this, where the left-hand side is the rotated image of the right-hand side. How do we use the equation to decide if a function is an even function? To decide if a function is an even function or an odd function, we need to start with f of minus x for any number x. Put the equation in. In this case, f of x is x squared, so f of minus x is minus x squared. Rearrange this, we get x squared, or f of x. Because f of minus x and f of x are the same, they're equal, this must be even. Next, I want to show that this function is an odd function. If I want to show that it's odd, I need to start with f of minus x for any number x. I put the formula in, here it's minus x cubed, which I can rearrange to minus x cubed, or minus f of x. We have that f of minus x and minus f of x are the same. So this is an odd function. Another couple of examples. You, I assume, know that cos x is the same as cos of minus x. This means that cos is an even function. And you probably also know that sine of minus x is minus sine of x. This tells us that sine is an odd function. For an odd function, the minus sign can take outside of the function. Sine, we can take the minus sign outside. Cos minus sine, we can just delete, and we still have the same function. If we're trying to show that a function is not even and not odd, we don't need to do this for every single x. We only need to find one number where two equations are not satisfied. Have a look at the second example on this page. I want to show that this function is not even and it's not odd. I don't need to use every single x. I can just choose one number. And I'm going to choose the number x is equal to 2. You could choose, for this example, you could choose any non-zero number that you wanted. I just choose to use the number 2 because it's a nice number. I've calculated g of minus 2 is minus 1, and I've calculated that g of 2 is equal to 3. If this was an even function, we would have g of minus 2 is equal to minus g of 2. But we don't have this. This is not true, so this function is not even. If this function was odd, we would have that g of minus 2 is the same as g of 2. But again, we don't have this, so this function is not odd. Therefore, this function is not even and it's not odd. I hope this answers your question. Are there any more questions? If you don't have any questions, you're welcome to leave whenever you wish. If you think of a question later, you can ask me using the discussion board. Yes, we have homeworks. There are currently 2 homeworks. And if you go to OLearn and click on the course material section, you will find homework 1 and homework 2. Okay, if there are no more questions, then we can finish the lesson here.